Hello again. This lecture is about the numeration system that we use, the one that we are used to, the one we take for granted, the one that we have to teach children. It's called the Hindu-Arabic numeration system. You probably know it better as place value or base 10 or something like that, but the official name is the Hindu-Arabic numeration system. To talk a little bit about this system, we're going to do an activity in class where we'll kind of just get rid of the symbols that you're used to, the 1, the 2, the 3, etc., and we will replace them with some new symbols. So let's take a look at the symbols that you may see in class in the very near future. Instead of the stick that we're used to using, the stick shape that represents 1, we're going to use this one. Instead of a curly little stick, we're going to use this one for 2. And you can see all these different symbols that we're going to use instead of the ones we're used to. Now, just in case you've already forgotten, this is what we're used to. This is what we're going to use. Now, we're not going to do this right now, but I just want you to think about this before we do the activity in class. Are these symbols that we're used to using, are they any more or less abstract than these? What does this symbol look like that we're going to start using for a 2? In my mind, it kind of looks like a 6. How about 3? Well, to me, it kind of looks like a backwards S. How about this one? This will be a 4. That kind of looks like 2 parentheses having a party. How's that? Are they any more or less abstract than the symbols we use? If you've never seen a 3 before, does it look like a 3? It just looks like half a snowman. Ooh, an 8, that's a whole snowman. Does it look like 8 things? Does a 6 look like 6 things? They are incredibly abstract, no less abstract than these ones that I've placed on this page that we'll work on an activity with. This looks like a musical note. Does it look like 8 things? Not really, but does this look like 8 things? No, it doesn't. It's just an abstract symbol. So we have to spend quite a bit of time teaching these symbols. Beyond the symbols, though, our system has a method of working. And to describe our system, I want to show you why our system is a little bit better than previous systems. Now, our system's been around for almost 2,000 years, but there were many systems before ours. Now, ours is, again, the Hindu-Arabic system. I don't know if you knew that or not. It essentially began around 800 AD, and without too many changes, it's the same system we're using now. There's been a few variations, but typically we use 10 digits or symbols, and just those 10 digits, 0 through 9, we can use to make every possible number. Every single number consists of only those 10 symbols. All right, why is that a big deal? Well, let's talk about a couple systems that have existed in the past, and they are very simple systems, but there's some reasons ours is better. The ancient Egyptian system was an additive system, and the symbols that they used were pretty simple. For 1, they used a stick. For 2, they used 2 sticks. And for 3, they used 3 sticks, and so on and so forth, up to 9. Okay, once they got to 9, they decided, well, let's have just another symbol for 10, which is a croquet wicket. Then we don't need another symbol until we get to 100, because we can put lots of 10s together to make 20 or 30 or 40. We can put 10s and sticks together to make like a 28. So when we get to 100, instead of making 10 of these croquet wickets, we're going to make a whirlpool. That'll be 100. And we'll use those until we get up to a bigger number, like 1,000. And when we get to 1,000, in order to write 1,000, we'll use this symbol that's like a Pac-Man trophy. Yeah, that'll be it. That'll be our 1,000. And then we need another symbol when we get to 10,000. So that's the finger. It's a good finger, by the way, not the bad finger. If you want to write 10,000, you use a finger. 100,000, a frog. And if you want to write 1,000,000, well, that's an Egyptian touchdown. That's the symbol they use to represent 1,000,000. Then 10 million, there's another symbol. 100 million, there's another symbol. 1 billion, there's another symbol. There is an infinite number of symbols. Our system has 10. Theirs has an infinite number. Let's take the Egyptian system one step further, and I'll show you how they write numbers. This is a number. That's how they would write a number. A frog, a finger, 5 Pac-Man trophies, 6 whirlpools, 3 croquet wickets, and 9 sticks. That's a number. That's what it looks like. 100,000, 1 10,000, 5,000, 6 hundreds, 3 10s, and 9 1s. This is called an additive system because you just add as many symbols as you want. So this particular number is actually what we would consider 115,639. One hundred, 10, 15, or 5, I'm sorry, 639. 115,639. It's a pretty long number. Just imagine what the number 999,999 would look like. 900,000 would be 9 frogs. 90,000 would be 9 fingers. We'd have 9 Pac-Man trophies, 9 whirlpools, 9 wickets, and 9 sticks. That's ridiculous. And what's the next number after 999,999? Well, yeah, it's the Pac-Man trophy. It's 1,000,000. So they would go from a huge long number to a very short number, the next one. It's not an efficient system. It's really easy to write numbers. You just put as many as you need. But it's not efficient. Imagine trying to add numbers together using this system. An additive system is very simple. The Egyptians had one and they used it for thousands of years. Another system that is a little more complex is an example is the Chinese system, which is a multiplicative system. They again had a 1, a 2, a 3, up to 9. Then they had a 10. Then they had 100. They had 1,000. They had a 10,000. They have 100,000, a million, 10 million, 100 million, a billion, etc. They even had a 0, but they never use it for numbers. But they have a 0, and it looks like a 0. At least it looks like our 0. Their system is a little more complicated. They write vertically from top to bottom. So the first number, or the first amount, is here. It's a 7 and 1,000, which is 7,000. So they have 2 symbols for every what we would consider place. this is 8 hundreds, this is 2 tens, and this is 9. So this particular number would be 7,829. It's a multiplicative system because instead of putting 7 1,000s, they put 7 and 1,000, which tells us that we have 7,000. Okay, there's 2 symbols for every amount. Not sure if I described that real well, but I'm not sure it's terribly important other than to know that numbers are big. So remember, again, what would 999,999 look like? It would have probably close to 18 symbols. Our system is much more complex, but it's much more efficient as well. So here I have a number such as 4,687. Our system has a multiplicative and an additive feature to it. We have multiplication, which comes from the place value, and we have addition, which comes from putting the places together. So we have a place value, which is this thousands, hundreds, tens, and ones, but instead of having a symbol for each of those, we just put a number in the right place, and that tells us how many of those places we have. So 4,687 is written in this format. Oh, I lost my little pen here. There we go. It's written in this format, and it tells us a great deal. It tells us how many thousands. It tells us how many hundreds. It tells us how many tens. And it tells us how many ones. And because our system is so efficient, we don't need an infinite number of symbols. We only need 10. So you've seen an Egyptian system. Looks like this. A number looks like this. You've seen the Chinese system, where a number is written vertical. Looks like this. And you've seen our Hindu-Arabic numeration system. Our system is the best. And I have kind of like Letterman's top 10, but I have my top 5. John's top 5 reasons the Hindu-Arabic system is cool. Remember, I'm not teaching you this because you need to know. I'm teaching you this because you need to teach it to young children. You need to teach the system, so you need to understand it. So, number 5, algorithms are simple. Do you know what an algorithm is? An algorithm is like a step-by-step process where that we use where we might be adding two-digit numbers together. So we might have to put a number down and carry a number and add the tens columns, and that's called an algorithm. Can you imagine trying to figure out a step-by-step process with frogs and Pac-Man trophies and croquet wickets and numbers that are huge and then other numbers that are really small? It would be very difficult. Think of another system. Think of like Roman numerals. You've seen a clock with Roman numerals. Imagine developing a system, an algorithm that would be step by step. No matter what numbers you put together, you would always follow the same steps. It's not possible. Our system, it's possible. We learn one process and it works for huge numbers and it works for small numbers. So algorithms are simple. That's pretty cool. We typically only use 10 symbols. If you've ever experienced numbers in another base, like base 2 or base 5 or base 16, you may have used a different number of symbols. We use base 10 almost always, so we have 10 symbols. 0 through 9. That's pretty cool. We don't have to have an infinite number of symbols. We don't have to remember what the Egyptian touchdown represents. We just have 10 symbols. That's pretty cool. Whoops. Let's see. We have place value. Every place in a number has a value, and we have cardinal value. That is the number that tells us how much of the place we have. And then the final reason our system is really cool is because we have a 0, and we use it. Now think about this for a second. How many fish are on this page? Okay, sorry. How many pictures of fish are on this page? There are none. There are 0. So why on earth would we need a number or a symbol to tell us that there's nothing there? That's really, a 0 is really abstract to children. Teacher, there's no fish. Why would I need a number to show that there's no fish? Well, technically we don't need a number to show. We'd say there's nothing there. What we use 0 for is to hold one of those places open. So numbers are always the right size. If you don't have any hundreds in the Egyptian system, you just don't write any. In our system, you put a 0 in the hundreds place. That's complex, that's abstract, but it's cool because it makes our number system much simpler. Well, not simpler, much more efficient. That would be the best way to say it. So there's my top 5 list. Now don't forget that I have a pocket protector, and so I think things are cool that you probably don't think are cool. But that's my top 5 list. And just to reiterate a few things, the system typically groups by tens. Our numeration system, if we use base 10, groups by tens. You know how 10 ones are replaced by a 10. We never put 10 in the ones column. We put a 0 and a 1 in the tens. Same is true for hundreds, thousands, and 10,000s. And any number beyond. And another thing that you need to understand when you begin teaching our system, all right, beyond the fact that you don't tell 5- and 6-year-olds that they're using the Hindu Arabic numeration system, that would be ridiculous. Beyond that, you need to understand that our system goes from right to left. The smallest number, the smallest place is on the right, and it goes from right to left. But we read the number from left to right, and that's kind of confusing. So as a number gets bigger, it goes farther to the left. When we read words and we read books and sentences and things like that, we go from left to right. We read numbers that way, but they're not written that way. It's a very odd difference between numbers and writing. So understand that some children will write 463 as 634. Or whatever I said, 364. Our system's pretty cool, but it's really abstract. It's a tough system to teach. It helps us in the end, but it's not very simple to learn. When I taught elementary and middle school mathematics, I had 7th, 8th, and 9th graders that still couldn't do place value. It's that complex. So that ends our exciting edge of the seat lecture on the Hindu Arabic numeration system. So now you know.